So this is the last thing we talked about. I threw up a bunch of formulas and equations and said that they were related to certain surfaces, but we didn't really justify that idea. And I think I'm going to use the graphing calculator program to take a look at it a lot more detail. There is one surface, really popular surface that I didn't have time to discuss or to mention, introduce you to. Did it just turn blue? And so I want to add one more to this list of things. Where it kind of looks like a paraboloid, but one of them is a minus sign. So this is still called a paraboloid, but the idea behind calling these things paraboloids and something else is based on what we're going to define as traces. Have you guys heard of a trace? You know what a trace is for these graphs and three-dimensional surfaces? Okay. A trace is that if you cut a surface with a plane, and then it's going to intersect at some sort of curve. So maybe instead of just giving you this picture, we should talk about traces. So let's start this on a new page. And let's talk about a trace. A trace is when you take one of these variables, either the x, the y, or the z, and a lot of times we're going to choose a z. But you take one of these variables and you set it equal to a constant. And what that does is that, for example, if we take z as a variable and we set it equal to 0, you saying z is equal to 0 is essentially a plane, right? That's the xy plane. And what's going to happen when z is equal to 0, you're going to take your equation and then you're going to put 0 in for z, and then you're going to try to see what the resulting graph is going to look like. So this might look a little complicated, but if you bring everything to one side, you get x squared is equal to y squared. And if you do that square root business, this is one of those cases where when you take the square root, you have to consider the plus and minus. So if I graph this, x squared is equal to y squared, what am I going to get?
A double x. If you take the square root of the side, it's plus or minus a line.
It's plus or minus, y is equal to plus or minus x. You know, the negative sign can go on either side. But yes, it's going to be y is equal to plus or minus x. So we can say that a trace for this graph on the xy plane, for this first one, would actually be 2 lines. Isn't that a wrestler or something? Maybe it's this. Sometimes we label it, so we can label it z is equal to 0. Okay, that's interesting. Now let's find another trace. So let's let z is equal to 1 this time and see how that's going to look like. So we'll let the z equal to 1, get x squared minus y squared. So this is why it is very important that you really get to know your conic sections. Because what is this? It's a hyperbola. One of them's a minus sign, right? So it's a hyperbola. I would say it's a hyperbola going up and down or side to side. So one way for me to think about this is that if I set x equal to 0, that's the y-axis, right? Whoops. If I set x equal to 0, I'm going to get 1 is equal to negative y squared. Am I going to have a solution for that? I'm not going to have a solution for that. So this is not going to pass through the y-axis. If I let y equal 0, that would be the x-axis, right? If I let y equal to 0, I get 1 is equal to x squared. And so that's plus and minus 1. So for this, I will have two intersections, plus and minus 1. So that's probably how my parabola or hyperbola will work out. Okay? So this is z is equal to 1 trace. Now I could go z is equal to 2. And if I want to make sure I make it look like a hyperbola, I would divide everything, and so I'll have it intersect at plus and minus square root of 2. But in any case, that's just going to be another hyperbola opening sideways again. Now I'm drawing this just on the xy plane, so that's kind of hard to visualize because what I eventually want to do is I eventually want to make this look like 3 dimensions. And when we're dealing with hyperbolas, it's going to get really weird. So before we get weirded out, let's try something else. Let's try z is equal to negative 1. So I have negative 1 is equal to x squared minus y squared. What kind of a graph is this? So this is another hyperbola. It's going up and down. If we want to make it look like a hyperbola where the constant side is equal to positive 1, we can just divide out by a negative, and then I'll get 1 is equal to y squared minus x squared. And so this will be opening up and down. Yeah.
So what I'm understanding is that this is basically traced are just like snapshots of different layers.
Yes,
And
snapshots
then-
of different layers.
Okay. And then put together.
Yes.
Okay.
Put together is actually called something else. We will define this later on. As a level curve. But we'll get into that with a little bit more detail in chapter 14. But now I'm going to attempt to try to draw this in 3 dimensions.
It looks like topography.
Level curves are exactly topography.
Oh, okay.
Before I do it in 3 dimensions, let's take a look at other traces. Sorry. I hope you guys are taking notes in pencil. If not, too bad. So we have traces when z is equal to a constant, but we also have other traces when x or y is equal to a constant. So let's try a couple of traces along the x. Let's say x is equal to 0. So when x is equal to 0, I would have z is equal to 0 minus y squared. So z is equal to essentially minus y squared. What kind of a graph is that?
It's a sideways parabola. So I guess it doesn't matter, it's a parabola.
It's a parabola. But let's put it, let me draw the axis for this. Let's put it on the, I guess it would make sense to put it, since we're letting x equal a constant, it makes sense to put this on a YZ axis. And what kind of graph is this? Z is your dependent variable, y is your independent variable. Z is equal to negative y squared. Graph?
Upside down parabola.
Parabola, upside down, negative sign, so it's an upside down parabola. X is equal to 0, upside down parabola. That's 0, but we can have other traces as well. Let's let x equal to 1. What is this going to be? Z is equal to 1 minus y squared. What is this? Parabola? Still upside down parabola, but what happened? Shifted up or down? Up 1. So x is equal to 1. How about x equals negative 1? Z is equal to, so x is being squared, so that's 1 minus y squared again. Same thing, right? So it looks like I'll have the same trace whether I have positive or negative. No, because if x is equal to negative 1, you negative 1, and then we're going to square that, so it becomes positive again. So it's still going to shift the same direction. All right, let's try traces for the y. Y is equal to 0. So we have z is equal to x squared minus 0, so z is equal to x squared. And what is that? Parabola. So on my xz plane, parabola going up. When y is equal to 1, I have z is equal to x squared minus 1 squared. Shifted down, same parabola, shifted down. All right, so if we make our cuts along the x or the y, or if we let x or y be constants, we're going to get parabolas. And if we make our cuts along the z, we're going to get hyperbolas. So this surface is a really, really famous surface called the hyperbolic paraboloid. Technically, it's a paraboloid because it's based on parabolas and it has x squared plus y squared, and z is not being squared. So technically, it's a paraboloid. And if you make your cuts along the z-axis or along the along the z-axis, you'll get hyperbolas. So that's why it's called the hyperbolic paraboloid. This is also known as, anybody?
Is that the thing in the Grand Central Station where you have like 4 volts and then it comes
No.
over it? Oh, no.
No.
I thought so.
Close. No, it's not close. But anybody know what this is called? Claire? You should know. We talked about it over the summer.
Oh.
On a horse.
What?
On a saddle?
Not a saddle. It has a shape.
What?
Right.
What is a saddle? Look at a saddle. Imagine how a saddle looks like. If you see where your legs go down, it's like an upside down parabola. If you go back and front, where your legs are, your front and your back. If you get off the saddle, you see an upright parabola, right? Now, probably hard to cut the saddle along the Z, but if you imagine cutting the parabola, the saddle along the Z, you'll get hyperbolas. So, this is the graph that we're looking at. Now, the first thing we did was we cut it with a z is equal to 0 plane, right? And if you cut it with a z is equal to 0 plane and take a look at it from the top, there's those two lines that we were just talking about. Now, if you move up along the z-axis, these are your, okay, can you guys see? I don't know if transparency on this will help. You'll see where they intersect are hyperbolas. And then if we take a look at it from one view, and then we take a look at this from as a cut negative one, now the hyperbola is opening up a separate way. Can you guys see this? Let's see. So the graph on the right-hand side gives you the trace image of the intersection that you're getting from the plane and the surface. And as I move that image around, or as I move that plane around, you're going to get different images that we're getting. So right at 0, you're going to get those two lines that we had drawn. And when we go less than 0 or greater than 0, we're going to get those hyperbolas opening sideways, and if we go less than 0, we're going to get those hyperbolas opening up and down. Now can you see? So these are traces when we make our cuts along the XY plane. All right? See if we can just do a quick picture of this. Now, those are the traces along the z-axis. But we also have traces along the x and then the y. So for that, with this particular program, I'm going to have to cheat a little bit. I'm still going to call this x squared minus y squared is equal to z squared. I'll have, this time let's take a look at it from the x point of view. Is that the first thing we did? X is equal to 0? So my cuts now are going to go along the x-axis, so they're vertical, right? And this first cut is on the y and the z plane. But I want my graph to reflect the idea that I'm making the cut along the x-axis. So I need to get this x here as my n, and I don't know if this is going to work like this. Kind of works. So as I make the cut, you can see if you make those cuts vertical, it's going up along the saddle, and I'm going to get parabolas that are pointing downward that are going up and down, depending on where you make your cut. Right? Yeah.
So, like, is there any way to actually find, just mathematically, like, take a derivative or something, to find that minimum point where the parabola is at its lowest?
Yes.
Okay.
We're not going to do that today.
Okay.
Okay, so this is your typical cut along the x. And then if we change it with respect to y, and then again I have to cheat a little bit and play around with this. This time we're going to get parabolas that are pointing upward. So I don't know if it's hard to see, but the parabola pointing upward is this business over here. Okay? So that's your hyperbolic paraboloids. That wasn't very good. Okay, so those are the traces. The idea behind the traces is that you set one of the variables equal to a constant, and if it's a z variable, then your traces are parallel to the xy plane. And then you have to try to identify what resulting two-dimensional graph you're going to have. And that's going to be the two-dimensional graph that you would imagine this surface would have after you make a cut. And then you could do that along the x also and along the y to make your cuts. Okay? Any questions? Yes? I know the paraboloids do. I don't know about the saddle. I don't know. Yeah, they don't seem to, I don't think I've read anywhere about focus for the quadric surfaces. Okay, any questions? No? So now that you know all these surfaces, all that's left for you to do is do your homework. And, yeah?
13.1, there's like an intersection of the sphere and something else.
13.1? Oh, is that a lab?
Yeah, it's a
Oh.
Or was it a sphere thing? No, there was no sphere thing in the lab.
All right. Well, I was. I was going to take a look at. These are some of the questions that you have for this section, where you're supposed to just look at an equation, identify it, and then imagine how the graph would look like. So I probably should talk a little bit more about the hyperboloids. So let's take a look at, for example, number 7, to try to see if we can answer this question. So it says use traces to sketch the surface. So the first thing to note is that this kind of doesn't look like any of the things that we've talked about, well, until we mess around with it and play around with it and divide by 12, for example. And then we can see that it actually does look like one of those surfaces. So let's start by rewriting your surface. I'm hoping that there's very little of completing the square business here, because you know, how'd you guys do with completing the square? You guys remember all that stuff?
Yes.
Okay. All right. So when you think about completing the square, that means there's a shift in your center point, and your center is not in the middle anymore. So, I mean, I think it's still easy to deal with, but I think most of these problems, they don't have that shifting anymore, so you won't have to worry too much about completing the square. But you do have to take an equation like this and imagine it looking like one of the surfaces that I talked about in that one page, and so you can somehow rewrite this to make it look like one of those surfaces. So if we divide everything by 12, for example, we're going to have x squared over 4. We can call that 2 squared, minus, and then this is just a y squared over 1 if you want, and then a z squared over square root of 12 squared. So that's just 12, and that's equal to 1. So we have, if they were all pluses, if they all had the same sign, then that means we're all good. This is an ellipsoid, 3-dimensional. But what we have to note here is that we have a negative sign for the y, and so this is going to be a hyperboloid. Now, I didn't discuss whether this could be a hyperboloid of 1 sheet or 2 sheets. I didn't really talk about 1 sheet, 2 sheet business, but we could talk about that now. The idea behind 1 sheet or 2 sheets is based on how many negative signs you have. Is it? Or something else? Let me say something else right now, because I don't remember. But what you would do is you would figure out if this thing's going to intersect a particular plane. So because y is your kind of like your negative axis, I would be interested to see what happens on the xz plane, on the xz plane. And when I say xz plane, what equation am I talking about? Y equals 0. So xz plane is equivalent to saying y is equal to 0. So I would be interested to see what happens when y is equal to 0. So let's set y equal to 0. You got x squared over 2 squared plus z squared over square root of 12 squared is equal to 1. And what does that remind you of? This is an ellipse.
Just choose one.
It's 2 dimensions. It has just the x and z, right? And it's something squared over, it's a variable squared over a squared, variable squared over b squared is equal to 1. So this is an ellipse. If one of them had a negative, it would be hyperbola. And it's 2-dimensional. So we just said that it is on the xz plane. And we could be a little bit more precise now. X is going to intersect at 2, and z, what's the square root of 12 about? That's 3 point something. It's bigger than 3. Whoops. So I have a trace on the xz plane, and it would look something like this. So because there is, in fact, a trace on the xz plane, tells me that this should be a hyperboloid of one sheet. And a hyperboloid of one sheet just means it's a one surface sheet. It's a one surface thing. It's a continuous one sheet surface. As opposed to 2 sheets where you need 2 pieces of paper to make your surface. I guess a hyperboloid of 2 sheets, you need 2 pieces of paper to make it. Hyperboloid of 1 sheet, you only need 1 piece of paper to make it. All right? So this should be enough to go with. I mean, we can let y equal to 1, 2, 3, and et cetera, and then we'll get some other, a bunch of other ellipses. But if you imagine drawing this in 3 dimensions now, this ellipse that we drew was on the xz plane, so it kind of looked like this. And then if we drew more ellipses, it'll probably end up looking like this. And so your hyperboloid of one sheet would look like this, kind of like a sideways silo, nuclear generator plant. Chinese finger trap. Okay? So another observation is that since y was the one with a negative sign, or y was the one with a different sign, it opens along the y, and then your traces are along the xz. All right. Now let's see if we can answer the question that they ask here. Here it's the y that's opening up on this multiple choice here, so I'll probably choose that first one. This is a hyperboloid of 2 sheets, it looks like. There's 2 pieces. This is just a paraboloid, and this is an ellipsoid. So we found out that this is, in fact, a hyperboloid of just 1 sheet. And then we can say hyperboloid of 1 sheet. So a hyperboloid of 2 sheets will just mean that there's 2 variables with a negative sign. That's the difference. So I won't do a whole new problem for that, but an example of a hyperboloid of 2 sheets would be something like 3x squared minus 12y squared minus z squared is equal to 12. So this case, this would be a hyperboloid of 2 sheets. Guess I should have done this in a different color. that's because x is the one with a different sign. If you let x is equal to 0, then you're going to have a negative number on the left side is equal to positive 12, which cannot happen. And so x equal to 0 will not have any intersection or any traces. And for this, without going to too much information, I'm just going to graph it. 3x squared minus 12y squared minus z squared equals 12. It looks like I need to zoom out. And at x is equal to 0, I see that my plane at x is equal to 0 is not intersecting this graph at all. So if I were to try to let x equal to 0 mathematically or algebraically, I'll get a negative number equals positive 12, which isn't going to happen. So doesn't want to go too far down. All right. Questions? Yeah.
But the, do you have like two negative values?
Yeah, I think in general, if you have two negative values, it's kind of tricky. Sometimes I put a negative on a constant on the other side. And so you got to think about that as bringing the negative over to the other side. So, but generally, that's the idea. If you know that this constant is positive 1, like normally we would like it to be, and then you got two negative signs, then it's a hyperboloid of two sheets. Okay? All right. Questions? Well, are we good for this section? So I highly recommend you going to the STEM Center or another lab that would have this graphing calculator program. This graphing calculator program is so easy. All you got to do is type in the equation, and then it draws a graph for you. You can search another online graphing calculator for surfaces, but very few of them allow you to write the x, the y, the z all on one side as a relation equal to a constant. And just like your handheld graphing calculator, if you wanted to draw an ellipse, you can't really draw an ellipse there because you'd have to draw half of the circle or half of the ellipse, the top half, and then you would draw the bottom half separately because it doesn't draw that whole thing as a relation. So that's the same idea for these types of calculators. But this particular one has the capability to be able to draw a graph if you have an x and a y anywhere, or and a z anywhere in the equation. They can all be on one side. They can be spread out in different sides, but it'll graph it for you. But the thing is, you need to do that. You can watch me do it in the screen in class, and it looks so cool, and you can get happy. But when you do it on your own, that's when you actually see the nuances of what happens if this was a negative, or what happens if this is a bigger constant, what happens to your graph. You really need to try that out. Otherwise, you're just watching a movie instead of being in the movie. I don't know what that means. All right. Let's take a look at that issue that you guys had with a lab, maybe?
Oh, no, so
13.1?
I was looking at it, and 13, for some reason, 13.1 is due before 12.6, which Yeah, I find that odd. I don't
Oh.
know what's going on there.
Yeah. So 12.6 should be due this Sunday.
Right.
Yeah.
Which is why we're trying 13.1 and we're getting, we're doing the homework for 13.1.
All right. So now would be the time where I'll start talking about 13.1. Which number?
I bet
All right, so I probably need to give you guys some information before jumping into this stuff. So 13.1, what's the title of that section? Vector functions, maybe? Is that what it's called? So the weird thing about this, and one of the things that I don't like about the way this book is set up is that they introduce vector functions as if it was something like totally new and amazing, but it's something that we've already been doing, and they just didn't call it vector functions. So what I want you to do is think back at the very beginning of the semester when we first started talking in 10.1 about parametric equations. So our famous set of parametric equations is x is equal to cosine t, y is equal to sine t. And they said that if you let t go from 0 to pi or something like that, or to 2 pi, then you would draw out a circle. So the fact that you're able to draw something out with this means that you're already working with what's called a vector function. So the thing about this is that if you just write it like a vector, I mean, a vector is something with an x and a y component, right? I know it's a direction and magnitude business, but it has an x and a y component. Or if we go 3 dimensions, it has an x, y, z component. So you can really rewrite this function, this parametric set of equations, as a vector function. And for some reason, they like using R for the function, but they don't solely use this. And sometimes they reserve R for a special type of vector. But a lot of times, they just write it like this. RT is equal to, and then they have this special vector notation. And then they put the x component in the x component, and then they put the y component in the y slot, and then now you have a vector function. Well, really, we've been doing this already. Okay, this is just parametric equations written differently. And I think what their point is that now that you have a vector function, we can do things to this. Each of these things represent your function. And we've dealt with functions, and the type of function that this is really a function of just one-dimensional function, x of t, y of t. So we can dig out all the functions that we learned from pre-calculus and just put it into these different slots, and then now we have a vector function. ln, the e to the t, any polynomial, and trig functions, put them into these slots, and then we have a vector function. Okay? One thing I do want to stress is that for a vector function, let's start off with a little background. So in pre-calc, you learned about functions f of x. Or sometimes we say y is equal to f of x. Right? And so what I want you to think about now is what is your set of possible inputs and what is your set of possible outputs. Now, if we think about it that way, we can think about the possible inputs as, for this type of function in pre-calculus, as any number, right? So just a set of real numbers. And so I'm going to use this notation a lot because we're going to start diving into functions that don't look like this. What this is saying is that your function f takes r, this is my symbol for a real number, and then outputs another real number. So your input is a real number. Your output is a real number. Now back then, it wasn't a big deal because that's the only choice we had. And so I don't know if you've ever seen this notation, but all the functions follow this input-output real number to a real number rule. Yeah?
So you're not talking about domain and range there. You're talking about like just a number going in.
Well, in a sense, we're talking about domain and range, but we're not. I'm not going to care about what part of the real number goes in the domain. Like, there's some functions that can only take between -1 to 1, or some functions that can only take positive numbers, or something like that. I'm not going to get that detailed, but I'm just saying these are the numbers. These are the types of numbers that we get to use, and then your output is going to be a real number. So, given this notation and this idea, what I can do is I can take a look at my new function r. What types of numbers can I put in here? Or what is my possible input for this r? 0 to 2 pi, but in general, it's what? Well, I was thinking 0 to 2 pi according to this, but in terms of the grand scheme of things, it's a real number, right? So I get to put in a real number, and that real number, the t, is the real number that I get to put in. Now, what is my output? Now, this is where it changes. What is my output for this case? So it's in this particular function, it's a cosine and a sine. But in terms of the notation that I'm using, what do you think would I write here? It's a vector. And in this particular case, it's a 2 vector, right? So I would say a vector in R2. So my input is a real number, and then we can even say that real number is t, and my output is a vector in 2 dimensions. Okay? So these are called vector functions or vector valued functions to say that your output is a vector. And then we can have a vector in 2 dimensions like this, and we can even have a vector in 3 dimensions if we just add on another component. Does that make sense? So I don't know if you've noticed, but when I was doing this back in chapter 10 and I used this program, I actually have to define a vector as my function. And so I have an xy vector, and if you've taken linear algebra, when you take linear algebra, you'll see that vectors can be written in a variety of ways, and writing it as a column matrix would be just another way to write a vector. and is equal to, and then I'll get another 2 vector and say cosine t and sine t. And if I just extend this past 1, like go to 2 pi, 0 to 2 pi, and then I have my circle. Yeah?
So, going back to notation, how do you notate that it's a vector in one dimension, but specifically a vector? Because I would think that would just be a real number again, but that would just be a function. Like, there's no way to differentiate between a vector and just a function.
Well, generally we don't do vectors in one dimension. Because a vector in one dimension is really just a number. It's going, back and forth. In terms of the direction, we get 2 directions, positive or negative. So instead of saying direction, we'll just say positive or negative for the direction. So the more interesting vectors are in 2 or more dimensions. Now, if I do this right, let's see if I can actually draw vectors. Oops. Let's start off by seeing if I can draw the points. Pi, 2 pi, 2.8, 6.28. Oops. So when you're drawing this, what's really happening is that you're not just putting points. You don't, before when we were thinking about parametric equations, you probably thought about just plotting points. But if you look at those points as vectors from the origin, you're really tracing it out with a vector function. You're really drawing a vector from 0 to whatever point you're pointing at, and then you're drawing it out like this. Okay? Some of the more interesting graphs that we had some wavy stuff. I don't know. I was going to try to do one of those, but I don't remember off the top of my head, so I'm not. But something more interesting is that you can bring this up to higher dimensions and then still call it a vector value function. So along the same lines of this particular function that we just draw, the circle, we can come up with another vector valued function. Let's call it r of t is equal to cosine t sine t. And then if I throw another one, and I think we talked about this before also, let's call it t. And I'm going to leave a little space here because I might want to scale it in terms of drawing this out, because when I draw this out, I want it to not be out of the picture. So I'm going to scale it by 1/10 or something. So imagine along the x and the y, what is this going to draw? If I just focus on the x and the y, it's going to draw a circle. Now if I let this go beyond 2 pi, it's going to keep drawing that circle. With me so far? Okay. Now, if I add a z component, where your z component is 1/10 t, or t, what's happening to that z component as you're drawing the circle? So this z component gives you the height, the z value of this vector, and if you keep going around in a circle along the x and the y, and your z is changing by going up, you're really just drawing a spring. Can you visualize that? All right? So you're really just drawing the spring. Or it's called a helix. you guys heard of helix? So if we take our graphing calculator program here and then just throw another component, well, just start new. This time it's a 3-vector. And then I don't want to restrict myself to just go from 0 to 2 pi. So I'm going to go from 0 to, I don't know, 100? No. What? 20? That ball's too big. Oh, I need to change my So if you just imagine this as a vector drawing something out, it's going to draw the thing out, and it's going to leave the trace. The trace that it's going to leave is a curve that defines this vector valued function. So what's important up here is not looking at this as a point, and in some sense the curve itself might not be important either, but what is important is looking at the vector that draws it out. And as you draw that out, you're going to leave a trace, and the trace that you're going to leave is that curve. Okay? So that's how we would want to think of a vector valued function. It's a drawing mechanism that uses a vector from the origin to some point, and then it draws something out, and then it leaves the trace there. Have you guys seen the 3D pen? You guys know what a 3D printer is, right? On a video of 3D pen. Encoding? Why does it need to be encoded?
You got this, you got this, you got this.
Okay, we're going up,
Come
we're
on,
going
come
up,
on,
we're
come
going
on,
up,
come
we're
on.
going.
Yeah, it's like if Apple created a glue gun.
Kind of, but it's kind of
I just want to see it done.
There we go. I'm getting it. I'm getting it.
What?
Yep.
Oh, there we go. There we
You're
go.
drawing it out, and you're leaving a trace.
I think we should note that both of us have made our living as
Kinda
illustrators,
like the
full-time
same idea.
illustrators.
Yeah.
You know, some
And
point
so
in space
far,
you're
this is
drawing
what
it out.
I've
The
come
only
up
thing
with.
that's different here is
And
that
this is
you're not
what
looking
I
at it
have.
as a
This
vector.
seems like something kids would do in camp.
Imagine
And the counselor would go talk to their girlfriend or boyfriend at this time.
I'm going to try the higher speed setting.
Oh, I've been doing the high speed
Oh,
all
really?
the time.
I've been doing the slower. Oh, okay.
John
that's-
McClaning this.
That.
Anyways. So the main difference between just calling this a vector function versus a parametric equation is that a set of parametric equations, you're actually dealing with three different things. You're dealing with the x value, the y value, and the z value. And you're dealing with them separately. With a vector valued function, you're calling that just one function that has all these components. Okay? So what can you do with a vector function? Well, turns out that you could do calculus with them. We could do calculus with f of x, right? We can find limits, we can find derivatives, we can find integrals of f of x. Well, if we take a look at each of those components separately, well, yeah, we can find derivatives, integrals, and limits of all these things separately. So why not think about finding the limits and derivatives and integrals of this whole thing together, but just looking at it component by component? So that is really the main purpose of putting this together into one thing called a vector function. All right, let's see that problem again. Number 3. It says, at what point does the helix intersect the sphere? Oh, there's another problem I wanted to do with lines and planes, and that's the intersecting lines and planes. We kind of did that, but not really in detail. But we get to do it with this one. So imagine a sphere, radius, what's the radius of the sphere? Square root of 17. And then a helix, that goes like a spring up and down. And so at some point, probably up here and probably somewhere down here, we're going to find some sort of intersection, right, of those things. So intersection, we've kind of already said that when we find an intersection, we set them equal to each other. Is there any way to set these things equal to each other that would make sense? I have a sphere and a helix. Any suggestions on how we might be able to set these things equal to each other? So if we break them into parametric equations with x, the y, and the z, and look, there's an x and a y and a z there, we can just put it together, right? So let's try that. We got x is equal to sine t, and that's going to be squared. Y is equal to cosine t, and that's going to be squared. And z is equal to t, and that's going to be squared, is equal to 17. So we basically took our equation with the x, y, and z and put in the appropriate x, y, and z values that we have. And good thing we know our trig, right? And that this is equal to 1. And then we solve for this So this is going to be t squared is equal to 16. Take the square root. You throw the plus and minus. Square root of 16 is 4. So when t is equal to 4,
You have to plug into those values, right, the vector?
yeah.
To get the points.
So t is equal to 4 tells us if we want to relate t with time, it tells us when we're going to intersect. So by putting it back into the parametric equation, so the vector equation, we're going to get our values. So the smaller t would be -4, and that's the z component right here. And then we want to put cosine of -4 and sine of -4. Small space. And then we want to put the other point, t is equal to +4 for our values. We have time to check, yeah? So sine -4, they put a parentheses here. Oh. You guys figure it out then. So that's the intersection between a curve and a space surface. Okay. So vector valued function is going to be another new tool for us. It all comes from vectors, but we've done parametric equations already. We want to just treat them as vectors. And now we can do stuff like take the dot of them, take the cross of them, aside from taking derivatives and integrals of them. So we'll march through all those things as we go along. Yeah? Yeah. So 12/6 will be due on Sunday. And 13/1 is still going to be due on Sunday.
But not 13/2.
I don't know. If I cover it tomorrow, then we'll see.